Good evening, everyone. Welcome to the course Control and Tuning Methods in Switch Mode Power Converters. I am Teja Golla. I am a fifth year research scholar working under Dr. Santanu Kapat at Embedded Power Management Lab, IIT Kharagpur. So, welcome to the problem solving session. Uh, Today is the week one problem solving session of this NPTEL course, and week one is about switch mode power converters and MATLAB simulation. So, in these sessions, first of all, these sessions will happen every Monday for the 12 weeks of this course. And on every Monday, it will be from 6 p.m. to 8 p.m. If I'm unavailable, then I'll let the NPTEL team know so that they will either prepone or postpone. And then you'll be informed about the change in the timings or the date ahead of the session so that you can be prepared before. So in these sessions, I'm planning to quickly summarize the topics that Sir has discussed in the week one, and also I'll solve a few problems. So in the previous years, I have taken problem solving session for a different set of course, and for this course, this is the first time. So I'll be taking 2 hour session every Monday from 6 p.m. to 8 p.m. and the meeting link remains the same. So we'll join this Zoom meeting every week on Monday, and then we'll have these sessions. So I'm in the chat. I'm giving some important links that you should keep with you. So first one is my YouTube channel where I'll be uploading the recorded videos. So first of all, these videos, these 2 hour sessions are recorded. So I'll edit them and then I'll upload to the YouTube channel. I'll try to upload it on the same day itself. So if the session is happening, say today, I'll try to upload it by today night. If I'm busy, then I'll try to upload by next day, but not uh, after 24 hours. I'll try to upload within 24 hours. And then the link to this Zoom meeting also I have attached there. So you can join this Zoom meeting. Also, NPTEL team will remind you every Sunday and they'll send you the meeting link. If there is any change, they'll also inform you. And I'll take notes. Whatever I'll be explaining or whatever I'll be solving, I'll upload to this drive. So you can save this drive link. So throughout this semester, I'll be using these three links. So the first one where you can access my videos, the second one where you can enter this Zoom session, third one where you can find the notes that I'll be preparing throughout these sessions. So in this session, I'll teach the basic concepts, quickly summarize whatever Sir has discussed in the entire week. So it may not be possible to teach each and every concept that Sir has taught in an entire week, but I'll brush up all the important concepts where you can ask doubts. If I miss anything and if you are not sure or not clear about any concept, you can ask me. I'll clarify your doubts. Then we'll also solve few problems so that it will help you to solve the assignments. So that's all about this session. Before we start, I think as it is a first day, one by one you can unmute yourself and give a brief introduction about yourself, your name, and where are you from, and what are you currently doing, BTech, MTech, or whatever you're doing job. And then you can also uh, discuss one or two lines about why you have taken this course, what is your objective or what is your final aim towards the end of this course, like what you are planning to learn, and also what you are expecting from this session, so that I can incorporate your suggestions and then we can move accordingly. So this will be more interactive. I will not be only talking. You should also ask questions. You should be more interactive so that you can learn and you can also get benefited. And we'll have a nice interaction discussion where you'll also be asking questions and I'll be addressing, and we'll also solve problems together. So if we make it more interactive, then it will be benefited for you as well as me, so that I'll not feel bored and you'll also get benefited from this session. So maybe I think Rahul can start. You can just briefly introduce about yourself.
Sure, Teja. So, good evening, all. So, my name is Rahul. I am currently pursuing MTech from Amrita University. I am currently based out of Pune location, and I'm pursuing MTech in automotive electronics. So, this course on the control and tuning, this is part of my curriculum for as a third semester of my like automotive electronics course. So what I hope to get out of this is understanding of the various switching techniques and the power electronics and how the same can be applied in the world of automotives.
Okay.
So that's my objective from this.
Okay.
Thank you.
Okay, Naveen, maybe you can introduce yourself briefly.
Good evening, sir.
Good evening.
My name is Naveen Kumar. I am from Anantapur. Actually, I am studying MTech in NPTEL. Actually, I want to learn for design of PA controllers for the high voltage and DC-DC converters from this course. Thank you.
Anushri, maybe you can introduce yourself.
Good evening, all. I am Anushri Shibindas. I am pursuing my PhD in Power Electronics in Nite Meenakshi Institute of Technology. Currently, I am first year. I opted this subject as a part of my coursework, and I am expecting this course will help me to continue.
Hello, Anushri, your voice is breaking.
That's all about me. Thank you.
Okay. Lakshmana?
Hello.
Yes. Yeah, now it is audible.
I am Anushri. I am pursuing my PhD first year now in Power Electronics.
Okay.
I opted this subject as a part of my coursework. Hello.
Yeah. Are you able to hear me?
Yes, sir.
Okay. And what are you like? What do you think will you learn out of this course?
Sorry, sir.
Like what? Like it is a part of your coursework, and what are you expecting from this course and these sessions? Like, this is your
Okay.
expectation.
I am expecting this subject will be helpful for solving the problem I am facing in my hardware
Okay.
analysis.
Okay. Okay. Thank you, Lakshmana.
Hello,
Yes,
everyone.
yes.
Am I audible?
Yeah.
Yeah, my name is Dr. Lakshman. I'm currently working at Amrita Vishwavidyapitham Chennai campus. So this course is quite interesting because our research group is working on switching mode power converter design for EV and other domain applications. So our student groups are really interested to develop some good simulation models following with the hardware. So I was asking my group students to take over this course. Maybe on behalf of them, I may be attending these sessions. The course is very interesting. The course teaching by professor is very innovative, very fundamental as well as research oriented. So that's the interest we have in the course. Thank you.
Very good. Thank you. And Shivam Verma, maybe you have joined a little bit late, so I have asked students to introduce about them briefly, their name and where are they from and what are they currently doing and why they have taken this course and what are they expecting out of this course, like what they are learning or why they have taken course. So just briefly. So you can introduce about yourself. Shivam Verma. Shivam, are you there? Okay, you are in the library. Okay, fine. Maybe we can move to Sonali. You can maybe write in the text box in the meantime. So we can move to Sonali.
Okay, good evening everyone. Myself Sonali Sabnis. Currently I am pursuing my PhD from NIT Surat. So this course I am taking as my coursework and I am doing work, my project work I am doing in the charging infrastructure for electric vehicle. So for that converter, switching purpose and converter study, I have selected this course.
Okay, thank you.
Thank you.
So now we can maybe move to Shubhendu.
Am I audible?
Yes.
Okay, so I'm Shubhendu. So I'm based on Kolkata. Currently, I'm pursuing my PhD at IIT Kharagpur, and my research field area is power management integrated circuit. So this course will help me in developing the control aspect of the power analysis. So that's why I opted for the course. Thank you.
So yeah, like based on whatever you have told me, so either you have taken it as a coursework or you have taken it as a part of your project. So in this course, we'll be learning more about control as well as the switch mode power converters, as well as the implementation of the controller of this SMPC in a MATLAB. So as we proceed from week 1 to week 12, we'll learn about many things. So in the beginning, sir will give a brief idea about switchboard power converters, and then we'll also learn parallelly about the MATLAB simulation, and then few modulation techniques, what type of controllers are available in the commercial products, and how to design the controller. So we'll also be learning about modeling techniques, because when we are trying to design a controller, we need to first model it. So modeling is very crucial, which we'll be learning thoroughly in this course. And once we learn model, we'll learn how to use that model to design controller for different type of controllers. And then once we design, we also need to implement in the MATLAB environment. So we'll also be learning how to do MATLAB simulation. So in the first week, it was a brief introduction about switch mode power converters. So sir has discussed about regulators, series as well as parallel. And then sir also moved on to basic converters like buck boost and buck boost to get started with the switch mode power converters. And sir has also just started the MATLAB simulation. So that MATLAB simulation part will not touch in this week. We'll discuss more simulation from the next week, because in the first week, sir has not shown like the simulation of all the converters. It is just a brief introduction, so that you can learn from the lectures itself. But moving to the next week, where we'll be implementing the controller as well as the overall converters, I'll also be discussing about the simulation. So if you face any difficulty in the simulation, you keep it ready so we can discuss in the next week. But in this week, we'll start with the brief introduction about what sir has discussed, which are regulators as well as few switch mode power converters. Okay, so I will share my screen. Let me know once you are able to see my screen. Are you able to see my screen?
Yes, it is
Okay.
visible.
Okay. Okay. So whoever has joined late, I am Teja Golla. I'm a research scholar working under Dr. Kharagpur, who is also the PI of this course, and I am from IIT Kharagpur. And this session will happen on every Monday, 6 to 8 p.m. And I have also shared few links in the chat box. I hope everyone is able to access the links. So I have shared my YouTube channel where I'll be uploading this video, preferably on the same day. I'll try to upload by Monday, right? But if I am busy with some other work, then I'll try to upload by Tuesday. And then this meeting happened in the same Zoom meeting. So you can also save the link, and also I'll be uploading the notes in the drive. I have given the drive link. So once I upload the video to YouTube, I'll also upload the notes to my drive. So you can access the notes there. And if by any chance, if you are busy with your work and are not able to attend the session, then you can always go through the recorded video, which will be available on my YouTube. So if you have any questions, you can ask, else we can move on to the discussion. Like I'll briefly summarize. Any questions you have till now?
Teja, there is a meeting scheduled for tomorrow as well. I can
Yes,
see.
yes,
Is that?
yes.
Yeah.
Yes. So
So
like
Monday and Tuesday. Yeah.
yes. So we are two TS, myself Teja and my friend Kelvin is also working under Professor Santanu Kapat. So he will also be taking the sessions on this same course. So if you are interested, you can attend both, or you can attend any one of them depending upon your availability. So if we are unable to discuss something, or if you have some more questions that we could not cover today, then you can also ask him, and he'll also be there to help you. So if you can provide us feedback that if you are expecting this, you want more of simulation and less of summarizing the content, then we'll adapt accordingly, so that we can spend more time on what you are weak, so that you can strengthen in those aspects. So the plan is I'll
So his
yes,
so
yes.
his lectures also will be recorded?
Yes. His lectures also will be recorded, and he will also upload to his YouTube channel. So both the lectures will be recorded and uploaded. You can access them anytime, and they're open to everyone.
Okay.
So in my previous sessions, the formula that I have followed is I'll try to summarize what sir has taught quickly, mainly highlighting the important aspects. And then if you have any further queries, you can also ask. Then I solve few problems, so that if you face any difficulty in applying the concepts that you have learned, then you can also ask questions. And through problem solving, we can learn the application of the concept, how we are applying the knowledge that we have learned. So if you don't have any further queries, then we can start.
Yes, we can see.
First, we'll discuss about the series voltage regulator. So in series voltage regulator, we have one series resistance, and then we have the load, and then here is the input to the regulator. So we need an output at the V naught, and then the input is say V in, and then say this is RS, and say this is load RL. So can you tell me what will be V naught in terms of V in and these resistors?
RL into RL plus RL divided by RS plus RL.
Yes. So V naught will be RL upon RL plus
Multiplied by V, definitely.
RS, yes, multiplied by V in. So now if we call the voltage gain as KV, which is V0 by V in, then we can get the voltage gain is RL by RL plus RS. So this is the voltage gain. So once we give this circuit and ask what is the voltage gain, we can tell. So if you want to vary the voltage gain, we have to adjust RS accordingly, because load resistance we cannot vary. Load is what we connected, so we don't have control over that. So we can vary RS so that the voltage gain will vary. So now if I ask you, can you calculate the efficiency of this circuit? How can we calculate the efficiency? Anyone?
Same as KV, right?
Yes, yes. So if you see the current that is being flown to the output, say we call it I naught, is same as the input current. So we know the efficiency is output power by input power, and output power is V naught into I naught. Input power is V in into I naught. So I naught get cancelled. So we'll get efficiency is nothing but V naught by V in. So my efficiency is nothing but KV. So if I ask efficiency, then it is nothing but KV. So the efficiency of this is RL by RL plus RS. So depending upon the ratio, efficiency will be, let's say if my KV is 1 by 5, then the efficiency is 20%. So it is not efficient in that sense. If the voltage gain is less, then the efficiency will be very poor. So it will be more efficient if the voltage gain is close to 1. Which is also understood, because if the drop across RS is high, then there will be a lot of power loss, because basically this is my output power. So the converter will be more efficient if I can get maximum power from this source, which means this is having more voltage, because current is same in both the resistance. So the output power will be more when V naught is more than voltage across this. So this is like a voltage drop. So whenever RS is small, which means the voltage gain is close to 1, then it will be more efficient. But throughout the entire range of kV, it is not efficient. As the kV reduces, efficiency will also reduce. So is this clear? Or do you have any doubts?
This is clear.
Okay. So now we'll
Yes,
go to...
it is clear.
Okay. So if you have doubts, you can stop me at any time and you can ask the doubts, so that we'll clarify the doubts and then we can proceed further. Now we'll move to shunt voltage regulator. In the shunt voltage regulator, we have the similar kind of circuit, but here we have a current source. Then there is load. So this is the input voltage, this is RS, and this is RL, and then this is, I am calling it as some shunt, right? So I am calling it as IS, and this voltage is plus minus V naught. So now if I want to calculate V naught in this case, how can I calculate? How to solve the circuit? And say this current is I naught.
So output will be VL time IS because that's the current source.
VL time?
It will be VL time IS. Let me calculate.
So anyone like how to solve this circuit? I don't want in terms of
So you
I
can
know.
do. So it will be basically you can use superimposition. For
Okay.
V in you will have a component of current that will be V in by RS plus RL. And
Yes.
because of IS you will have 1 volt another current, so you can just sum them up.
Yes.
By
Yes.
doing that you can calculate.
Yeah. Very good. You are right. So that is one way of doing. So we can let us do superposition like how you have mentioned. So if we consider V in, so V naught will have V01 plus V02. So V01 is because of the input voltage. Then you know that it is RL by RL plus RS into V in, right? Agree?
Yeah.
Yeah. So now if we see V in has positive terminal here. So because of V in, V naught will also have the same polarity. But if you see current is going from top to bottom, so the current will flow in this direction, right? So there will be positive terminal at the bottom. So because of the current, we'll have one negative symbol. So we'll have minus, and the current will be RS. In the RL, current will be RS by RL plus RS into current value is IS. So this is the current that is flowing in RL. Now, if you want to get the voltage, so this entire thing will be multiplied by RL, right? Agree? Is this clear, or do you want me to explain clearly this step, the blue color?
Sir, can you please explain in detail?
Okay, so if I consider the current source, let me redraw the circuit. So this is my resistance, this is my current, and this is my another resistance. We are applying superposition. So this is RS, this is IS, and this is RL. So now I can calculate the current through my RL, right? So what is the current through RL? It is nothing but RS by RS plus RL into IS, right? Agree? Hello? Is this clear? Current through RL?
Yes.
Now, if I
Yes,
want to
yes.
calculate the voltage across RL, I will multiply this by RL, right? But this is the polarity I'll
Yes.
get. So I'm keeping a minus because according to me, top terminal is plus and bottom terminal is minus. So that's why I have put one minus, and this is the expression that I'm getting.
Teja, you can do it in a different manner also.
Yes,
You
we
can
can do
think
in a
from
different manner.
when I mean for the second part, rather than making it complex. So you see, from IS point of view, you have two resistors there in parallel. So basically
Yes.
IS times RS parallel RS. So final expression is exactly same as that.
Yes, that also we can do because RS and RL are parallel. We can get RS into RL by RS plus RL into IS. So yeah, both are, yeah, you're right. Okay, so now if we solve this, we'll get V0 is nothing but RL. If I take common, I will get V in minus RS IS by RL plus RS. So if I further simplify, I will get KV is nothing but V input minus RS IS by 1 plus RS by RL. Agree, everyone? Is this clear?
Yes.
Okay, now in this case, how to calculate the efficiency? So how can we calculate efficiency?
So that will be basically output power by input power, right?
Yes,
So
yes.
you can calculate that way.
Yeah. So if we like, let me call this I naught. So let me also call this I in. Okay. So now if I call this I naught and I in, I know that efficiency is nothing but V0 into I0 by V in into I in. And V0 by V in is something I already know, which is kV. Now I have to calculate I0 by I in. So now I need to calculate I0 and I also have to calculate I in, and then I can get the expression. But I know that I in is nothing but IS plus I0, right? So I can write that. So I can get kV into I0 by I0 plus IS. Is this clear for everyone?
Yeah.
Is this step clear for
Sir,
everyone?
that KV, sir, one doubt.
Yes, yes.
Sir, that KV expression that you have written, numerator is a voltage, but denominator is a resistance. It could be unitless, right?
Yes. Okay. So you are saying that it should be unitless. Oh, sorry. By V in will be there, na? My mistake. So you are right. So I have to divide it by V in. So there will be V in here. You are right. I forgot to divide by V in. So here there will be V in. Yeah, you are right. V0 by V in, right? So I have to divide this by V in. So I forgot to write V in here. Now is this clear?
Yes, sir. Yes. Okay.
So now everyone got this expression, right? kV into I0 by I0 plus IS. Is this step clear for everyone?
Yeah.
Hello.
Yes.
Okay. So now how can I calculate I0?
I0 is V0 by R.
Yes,
RL.
V0 by RL. Yeah, very good. So let us do that only. So let us substitute I0 as V0 by RL. So we'll have kV into V0 by RL by V0 by RL plus IS. So now if we simplify it, we'll get kV into V0 by V0 plus Rn into IS. So now what we can do is we can substitute V0 here. So if we substitute V0 here, what will we get? We'll substitute this RL into V in minus RS IS by RL plus RS. So or we can just simplify that expression. So we have V0 by V0 plus RL into IS. So V0 is what? RL into V in minus RSIS. RL into V in minus RSIS by RL plus RS. Right? Yes. And one more thing, as I don't have premium account for this Zoom meeting, so it will be automatically logged out after every 40 minutes. So once the meeting is ended, I'll restart it. I can restart it because maximum time is 40 minutes. So I think the 40 minutes is about to end soon. Within a minute, the meeting will end uh, automatically. Then I'll rejoin. You also rejoin back. So we'll have to join twice. So from 6 to 6:40 or 6:35 because I have joined 5 minutes before. Once the meeting will end, and then next 40 minutes will join, and then it will end. And in the last 40 minutes, like the session will be over. So kindly keep this in mind. I'll be reminding you. So there is less than a minute. So within a minute, the meeting will end. Once it ends, please join there. RL into V minus RSIS by RL plus IS. So plus RL into IS. Right. So now if you simplify this, I'm simplifying, you also simplify with me. You can first of all cancel RL. So let us cancel RL. So RL gets cancelled. And then if you take the denominator common, then you will get in the numerator V in minus RSIS by, in the denominator, RSIS minus RSIS will get cancelled. So we will get V in plus RLIS. Is this clear? So is this clear, everyone? How I'm calculating this? Okay. So now my efficiency is kV into I naught by I naught plus IS. So if I do that, I'll get my efficiency. Efficiency is nothing but kV into V in minus RSIS by V in plus RLIS. So is this clear? How we are calculating? Any queries you have until this point?
So in this case, your power
Yes.
efficiency depends on your input voltage. In earlier, it was not.
Yes. So in earlier case, it is not dependent on the input voltage. But yeah, you are absolutely right. Here, one issue is efficiency is poor. Efficiency is poor at small kV or when kV is small. Okay. So here, if you see,
Also, I see
yeah.
one thing. I don't
Yes,
know if it's
yes.
correct or not. So the expression contains one negative term in the numerator, right? So is
Yes.
it possible that efficiency can go negative? I'm just asking from the expression. Looks like that is possible.
Yes, so it depends upon how RS and IS will consider. So, like if we consider like V in smaller than RS and IS, you have to also check whether that is possible or not, right? Then only you can like when is this possible? When V in minus RS into IS. So then there will be a negative voltage across this current source, right? Say, for example, so there is no RL connected, right? And then we have VIN, we have RS, and then we have IS. So then the voltage across current source will be VIN minus RS into IS, right? So if we are considering VIN to be less than RS and IS, then the voltage across the current source is negative. So if we are able to build a current source, then we can get a negative source. But usually this voltage cannot be negative. So that's why we will not get a negative voltage in this circuit.
For very low V in it is possible, right? For very low V in and very high IF, that is
Yes,
possible.
yes. But in that case, the voltage across the ISV is negative. So if the current source can work in that condition, then yes, theoretically it is possible. But practically, you should check whether this can be implementable or not.
Yeah, that's a nice sketch.
Yes. But here, another drawback is even if there is no load, there will be loss in the circuit because there is this current source. So there will be always current flowing through this RS, and then there will be loss in RS even when load is not connected. Whereas here, if there is no load connected, there is no loss in the circuit. But here there will be loss even when there is no load. So that is one of the drawbacks of the circuit, which is uh, non-zero loss even when RL is disconnected. So there will be minimum loss that is always there even when the load is disconnected. So IS will be flowing through RS. So the loss will be IS square into RS. So that loss is there even when the load is connected. Even when we are not supplying any power, there is still loss in the circuit. Whereas in the circuit, it is not there. So that is another difference. So is this clear? Shunt-based voltage regulator? Hello? Hello?
Yes, you can move to next topic.
Okay. So next one is the capacitive voltage regulator. In the case of capacitive voltage regulator, we use capacitors and switches. So say I have one circuit like this. I have connected two capacitors. Say both the capacitors are not equal and this is my output cell. So I have input V in and then say capacitor C1 and then C2. This is my V0. So how do I calculate V0? Anyone?
Vn into C1 by C1 plus C2.
Yes. So at the steady state, both the capacitors will have same charge. So the capacitors will reach the steady state once both the capacitors have same charge. So if we are considering this voltage to be, say, this is V0, then this will be V in minus V0. So now we can apply the charge balance, which is Q1 equals to Q2. So once the charge remains same, it reaches steady state. So we'll have C1 into V in minus V0, which is C2 into V0. So from this, you can get that V0 is nothing but C1 by C1 plus C2 into V1. So now if we calculate the voltage gain, we'll have C1 by C1 plus C2. Is this clear?
Yes.
Yes. But if we consider now, we are considering an ideal case where there is no load. So it will reach steady state and C2 will have this expression. I mean, voltage across C2 will have this expression, which is C1 by C1 plus C2 into V. Now say I have connected a load. So let us consider the same circuit. I have capacitor. So what happens is I have a load resistance here. C1, C2, R. So now it cannot reach one particular voltage and stay there because there is a discharging path for capacitor. So it will charge and discharge and charge and discharge, and then eventually it will reach a steady state. So in this case, we have to solve this circuit, and then we have to solve the differential equation to calculate what is my steady state voltage, because depending upon the resistance R, my steady state voltage will vary. So here we'll have to consider the voltage across this is equals to summation of voltage across this plus this. And also we know the equations, right? Say let us consider, if we have to solve this, say let us consider this one as I1 and this one as I2 and this one as I3. So now I know I1 is nothing but I2 plus I3 by applying KCL, and I1 is nothing but C1 into d Vc1 by dt, which is equals to I2 is nothing but C2 into, say this is my output voltage, which I am denoting as V0, So I'll get d v naught by dt plus R3 is nothing but V0 by R, right? Now, what is VC1? VC1 is nothing but V in minus V0. So now I'll get another expression, which is C1 into d by dt of V in minus V0 is equals to C2 into dV0 by dt plus V0 by R. Let us assume that V in is constant, so its derivative is 0. Then if we simplify the expression, then we'll get C1 plus C2 into dV0 by dt plus V0 by R is equals to 0. So this is the expression that we'll have to solve in order to get V0. So we'll get an exponential function and we'll solve one problem based on this. Then we can solve the differential equation. But this is the expression that we'll be getting for this type of circuit. So is this clear? How we'll solve these type of circuits?
Yes.
When there is a load resistor and when there is no load resistor. Okay, now we'll go to the buck boost as well as boost converters and also non-inverting buck boost. So in the case of buck converter, so does anyone know whether buck converter is a step-up converter or step-down converter or
Buck is
Step down converter.
step-down converter? Yes. Very good. So this is a step-down converter. Okay, I'll quickly draw the sample. So this is my wheel. This is my switch S. This is S bar. This is L. This is C. This is R. This is V naught. So you know what is a duty ratio, right? Say to the switch S, I am giving a gate pulse. This is time, and then the gate pulse is named as Q. And then if I'm giving such gate pulse. Okay. This time period is say T. And then this time period is say T on. Now I can write T on to be some fraction D into T because T on cannot be greater than T. T is the switching time period and then T on is the on time. So on time can be either maximum equal to T or it will be less. So it is less than or equal to 1 and it's a positive number. So from this I can say that 0 is less than or equal to D is less than or equal to 1. Considering a practical case where it cannot be negative. Also it cannot be more than the switching time period. So this D is nothing but duty ratio. And why it is very important? Because the voltage gain is a function of duty ratio. So that's why we write everything in terms of D. And D is the on time by switching time period. So D is, what is D here? D is T on by T. Fine. Is this clear?
Yes.
Okay. And do you know anyone has queries regarding the inductor volt second balance and capacitor charge balance? Do you know this or should I have to again briefly summarize? If you have no queries, then we can skip that part. Else I'll also quickly summarize what is that. Do you know, or like if you have query, you can ask, then I'll explain that and then we can go. Anyone who don't know about inductor volt second balance and capacitor charge balance? So should I skip that part, or do you have any doubts? Hello.
Please explain, sir.
Okay. So in this switching converter, when we reach the steady state, say I am talking about the inductor. So I know that voltage across inductor. So you know that inductor acts like a current source, and capacitor acts like a voltage source, right? So at the steady state, the voltage across the capacitor will reach certain value and stays there. Now because we are calling it a steady state, so it has reached some voltage and it is staying there. And inductor, it will have some current, and then it has reached steady state, so it has a fixed current. So now if we are talking about the voltage across inductor, which is VL, VL is what? L into DIL by dt, right? Right. So now if I consider like IL, which is 1 by L into VL into dt, right? Agree? Everyone?
Yes, yes.
Okay. Similarly, for capacitor, if I write IC is equals to C into dVc by dt. So my Vc is nothing but integral 1 by C into IC into dt. Agree?
Agree.
Yes. Okay. So now, before we go into the volt second balance as well as capacitor charge balance, if we draw the steady state waveform, we'll get the inductor current triangular as well as the capacitor current also triangular. Just let me quickly draw the waveform. So I'm considering this as the configuration. Okay. So whenever the switch is on, inductor is connected to the input. So the inductor will get charged, right? And then whenever S is off and S bar is connected, inductor will get discharged. So whenever the switch is on, say if I'm calling this as gate pulse Q, and this is I'm calling it as IL. So inductor current will be triangular in nature. So during this time it will charge, and then during this time it will discharge. During this time it will charge, during this time it will discharge. So at steady state, we can consider the average inductor current will be say IL. Right. So now what volt second balance says is, so what volt second balance says is average of the voltage across the inductor, say VL, into the time period. So inside the circle is 0, because if the average voltage is non-zero, then inductor current will keep on rising, right? Say if the voltage is positive across the inductor, then it will charge, right? So it will increase, current will increase. Similarly, if the voltage across the inductor is negative, then it will discharge. So current will decrease. But now we are not talking in the instantaneous point of view. We are talking as a steady state point of view. So we are talking about the average value. So the average value of the inductor current, it has reached a value IL. So effectively within a cycle, the voltage across the inductor, if we calculate the average, right? I should not say into T. If I talk about the average value, so if I talk about the average voltage across the inductor, it should be zero, because effectively inductor current is rising and falling, but in the sense of average, it is constant. So similarly, in the average sense, the voltage across the inductor should be zero. So this is called volt second balance, because the inductor current has reached steady state and it's a constant value. Because if the effective voltage or the average voltage is say positive, then IL will be increasing. Similarly, if VL is negative, then IL will be decreasing. The same will be applicable for the current as well. Same will be applicable for the capacitor voltage. So let us not get into how the waveforms are coming at this point of time. We can discuss, but today we are just learning about how to apply volt second balance as well as the capacitor charge balance to get the gain ratio and output voltage current. So capacitor voltage will do something like that. Sorry. Let us draw the capacitor current. We'll get it something like this. So now if we draw the output voltage VC, say let us call it VC. So whenever IC is 0, so then the IC is 0 means slope of VC is 0. So it will reach the valley because IC is negative. So during this time, as IC is negative, VC will be discharging, and then here the derivative will be 0. Similarly, at this point, it will reach the peak because IC is positive, so the voltage will increase, and then again it will follow the similar kind of path. So again, we are saying that VC has reached steady state. So it means that the capacitor voltage in terms of average has reached a fixed value. I think someone's okay. Now, because it has reached a fixed value, it means the effective average of the capacitor current is also 0. So this is volt second balance. Now this is capacitor charge balance. Capacitor charge balance. So in the capacitor charge balance, we'll get the same thing, which is the average capacitor current is 0. Because if the effective average is positive, then the capacitor voltage will build up. Similarly, if the effective capacitor current, average capacitor current is negative, then the output voltage will fall. But when we say that it has reached steady state, it means the average voltage is constant and fixed. So it means the capacitor is effectively, or in terms of average, it is neither getting charged nor getting discharged. So IC average will be 0. Is this clear? Or you have any confusion? Hello.
It is clear, sir.
Okay. So now we'll have to apply this on this circuit. So when Q is on, can anyone tell me what is VL? When Q is on, what is VL?
Vn minus V0.
VL minus V0, very good. And when Q is 0?
Minus V0.
Minus V0, very good. So D prime is nothing but 1 minus D into Ts or T minus dt. Can anyone tell me what is IC? So let us call this current as IL and then call this current as I0. So now I need IC in terms of IL and I0. So what is IC when switch is on, when switch is off?
IL minus I0 in both cases.
Yes, IL minus I0 in both the cases. So is this clear for everyone? Or if you have any questions, please ask. Is this clear how we got these expressions from the circuit? We have checked when the switch is on, voltage across inductor is V in minus V0, and when the switch is off, voltage across the inductor is minus V0. But capacitor current remains same during DTS and 1 minus DTS. So is this step clear for everyone? Hello?
Yes, yes.
Okay. So now let us apply volt second balance. You can also apply along with me. And one more thing, whenever this session happens, don't just listen. You also start writing along with me so that you will, if you will face difficulty at some point of time, then you can understand where you are facing difficulty. So whenever I am solving problems, try to solve with me. So if we calculate the average VL, so it will be VL minus V0 into DTS plus minus V0 into 1 minus DTS by TS is equals to 0. So can you quickly calculate and tell me what is V0 in terms of V in? Sorry, this is not VL. My bad. This is V in. This is V in minus V0. So can you quickly calculate and tell me what is V0 in terms of V in? Anyone?
V0 equal to D into V.
Yes, very good. So V0 is equals to E into V in. So this is the conversion ratio. So I can also write it as KV is nothing but duty ratio D. Similarly, if I do capacitor charge balance equation as IL minus IC is same IL minus I0 in both the cases, I can directly write IL is nothing but IL or IL minus I0 is 0. Then only it will become 0. So IL is nothing but I0 and I0 is what? V0 by R and V0 is also known. So it is D into Vn by R. Clear? Is this clear? Or do you have any queries? No doubts? Hello.
Yes, sir, you can go ahead.
Okay, okay. Yeah, please respond so that I'll proceed as if someone is asking, then I'll have to wait. So please respond. So now we'll go to boost converter. So we'll quickly derive the expression for boost as well as buck boost. Then we'll solve few problems. So boost converter. So this is capacitor C. This is S bar, L, V, C, R, and V1. So now we can directly write the expression. So Can you tell me what is VL during DTS and during 1 minus DTS? So when this switch is on, what is the voltage across inductor? When S is on. What is the voltage across inductor?
Vn, right?
Yes,
When
V.
switch is on.
Yes, yes. Good. And when switch is off?
V minus V naught.
Yes, V in minus V. Very good. And say the capacitor current, let us call this IL and let us call this I0, which is V0 by R, of course, and let us call this IC. Okay, so now tell me what is IC when switch is on, DTS, and when switch is off, which is DTS. IC in terms of IL and I0.
During DTS, IC equals to I naught.
Are you sure?
Minus I naught.
Minus I. Yeah, very good. And then when the switch is off, S bar is on.
Minus I naught.
Sorry?
IL minus I naught.
I know. Yeah, very good. I hope everyone is following and everyone is able to understand how we get these expressions. If you have any queries, you can stop me. So now, once we get this expression, so for any converter, we'll have to first get the VL, IC. So for inductor, we'll have to find the voltage. For capacitor, we'll have to find the current. So once we get this expression, then we'll have to apply the charge balance equation. So let us apply volt second balance first. So it is average VL is 0. So average VL is 1 by TS into V in into D plus V in minus V0 into 1 minus D. Everything into TS is equals to 0. So TS gets cancelled. So can anyone tell me what will be the expression for V0 in terms of V in once you solve this? I need V0 in terms of V in.
1 by 1 minus D into Vn.
V in. Okay, so it is V in by 1 minus D. So now if we calculate the voltage gain, which is K root, is nothing but 1 by 1 minus D. Okay. So now let us apply capacitor charge balance. So we'll have 1 by TS into minus I naught DTS plus IL minus I0 into D prime TS is equals to 0. So now can you calculate what is IL in terms of I naught? Anyone? IL in terms of I naught. So I hope others are also following. Okay, let me check. Anusri, Arun, Naveen, Prasad, are you following? Rahul, Sonali.
Yeah, we are
Yes,
following. Yeah.
Okay, okay.
yes, we are for.
Yes. So what is IL in terms of I naught?
Your I naught plus IC, the sum of those will be IL, right?
Yes, yes. Not exactly. So IC is minus I naught during DTS and IC is IL minus I naught during D prime TS. So now we have applied charge balance. So the average of this is 0. So I have calculated the average of this and equated it to 0. Now solving this equation, we'll get a relation between I naught and IL. So I'm asking what is IL?
Okay. Oh. So IL is I naught by 1 minus D.
Yes, very good. So IL is I naught by 1 minus D. And what is I naught?
That is V naught by R.
V naught by R, and V naught is V in by 1 minus D. So we can get IL is V0 by R into 1 minus D square. Fine.
Yeah.
So this is how we can get the voltage gain as well as the inductor current expression for a boost converter. Let us also do it for buck boost before we proceed further for the problem solving. So let us do buck boost converter quickly. So this is S L V in S bar C R plus minus V0. So now let me know what is VL. So when we say VL, this is plus minus. So what is VL during DTS and 1 minus DTS? Kindly check the polarity, don't make any mistake. So what is VL during DTS and what is VL during 1 minus DTS?
In the first case, it will be V in.
V in, very good.
In the second case, it will be
There is less than a minute, so the meeting will end as we have completed another 40 minutes. So if this meeting ends, kindly join back, then we can continue the session.
in the second case, it will be V out, right?
V naught, yeah, very good. So I hope others are able to figure out. So when this is connected, V in is VL, and if this is connected, VL is V0. So that's how we are getting this. Now let us consider the direction for IL. So say this is IL, and this is IC, and this is I0. Can you tell IC? What is the expression for IC during DTS and 1 minus DTS? If this meeting ends, time. So what is IC? During DTS as well as 1 minus DTS?
In the first case, it will be minus I naught.
Yes, very good. In the
Right.
second case?
In the second one, it will be actually disconnected. It will be IL minus I naught, I guess.
Okay, can you check the directions of the currents and try again?
Oh, it's actually minus IL, minus IL, minus I naught.
I0, yeah. So that's why the direction is very important. When we are solving any circuit, first we have to consider the current direction as well as the voltage polarity, and then we have to solve, else we'll make mistakes. So if we do the volt second balance, we'll get 1 by TS into V in DTS plus V0 into D prime TS, which is equals to 0. So what will be V0 in terms of V?
Minus d by d prime.
Minus V in by minus V in into D by 1 minus D,
D
right?
prime. Yeah, 1
Yes.
minus d. Yeah.
Yes. So now if I calculate the voltage gain kV, it will be minus D by 1 minus D. So in this case, the output voltage will be negative. If the input is positive, output is negative. Okay. So now let us do the charge balance equation of the capacitor. So we'll get, so as both of them have minus, I can take the minus common. Minus 1 by Ts into I naught into D Ts plus IL minus I naught into D prime Ts is equals to 0. So now if you solve, can you tell me what is the value of I0 that we would be getting? Sorry, not I naught, IL. It should be IL in terms of I naught. So what is the value of IL in terms of I naught?
In your expression, it will be minus IL minus I naught, right? Oh, you have taken minus common.
Sorry,
Okay.
plus. Yeah. So this is plus. Yeah. Right. This would be plus. Minus I have taken common.
Mhm. Correct.
I hope everyone is also trying. Calculate IL in terms of I naught and due to ratio D, and let me know the expression.
So IL is minus I naught by 1 minus d.
Yes, very good. Minus I0 by 1 minus D. So now if we substitute I naught expression, then we'll get IL is nothing but there are two minus will get cancelled. So D into V0, sorry, V naught by R, right? So D into V in by R into 1 minus D whole square. Everyone agree? Or have I made any mistake? Kindly check if I have made mistake, let me know. So I naught is basically V naught by R. V naught is minus dV in by 1 minus D. So I have substituted it and then I got this expression in terms of R, D, and V.
Yeah.
Is this clear for everyone? Naveen, Anushri, Rahul, and Sonali. How we are calculating these expressions. Is this clear?
Clear, sir.
Yes. Okay. Now, if you are clear, let me just quickly summarize before we go for problem solving session. So today we have discussed briefly about different type of circuits and the input-output voltage relation, mainly the voltage gain as well as the efficiency. And we are not discussing about the MATLAB simulation in this week, but we'll definitely discuss in the upcoming weeks. So we have started with the series voltage regulator and we have seen what is the voltage gain as well as how the efficiency is. And then we have moved to shunt voltage regulator and here also we have seen the same. First we have calculated the voltage gain and then we have also discussed the efficiency as a function of this voltage gain. And then we have discussed about a capacitive voltage regulator circuit and then we have seen how the voltage will vary if there is a load connected and when there is no load connected. And then we moved on to a buck converter. So we have discussed thoroughly about what is duty ratio, how it is defined, and then also the volt second balance of an inductor and the capacitor charge balance equation, and then how to apply it to get the input output voltage relation, and also how to get the inductor current as a function of duty ratio V in as well as load resistor. Then we moved on to boost converter. We have applied the same volt second balance as well as the capacitor charge balance equation to get the voltage gain as well as the inductor current expression. Same thing we have done for buck boost converter and we got the expressions. Now let us move to problem solving session. So one question that I have considered is what sir has discussed about the MATLAB. Although I'm not showing the MATLAB uh, implementation, but we'll see how we can implement this in MATLAB. Say I want you to implement this block diagram, and I have given input as in. Say we need to use the MATLAB blocks, which is gain blocks as well as the integrator blocks. And then I want V naught to be found if I have given you in. So anyone, how can we find in terms of, sorry, V naught in terms of in using MATLAB block diagrams? So I want this to be implemented in MATLAB using the integrator block, which is 1 by S, as well as the gain blocks. So gain can be anything, R1, 1 by R1, 1 by R1, C1. So how can we proceed? So anyone, any idea, or should I give you hint? So I need basically V naught in terms of V in, I in, R1, C1, and integrator blocks 1 by S. So how can I proceed further? If you have any thought, you can just tell me so that if there is something wrong, I can correct, else we can proceed with your idea. Okay, should I give you hint?
Can I repeat the question again? I
Yes.
missed that.
So basically, this is the circuit. So I have considered this question as we are not discussing the MATLAB, but in today's, I mean, not today, in this week, sir has discussed how to implement a circuit in a MATLAB using the integrator block as well as gain block and constant block. So I have given this circuit and I am asking you to implement this using the block diagram. So the only blocks you can use is the integrator, which is 1 by S, some constant block for V, and then gain blocks for resistor and capacitor. So how can I start? How should I proceed?
So we can write in terms of like IR plus IC,
Okay.
split them out and write
Okay.
expression for both of them.
Yes. Yeah. That is one possibility. So let us proceed with whatever he has said. So IN is nothing but IR plus IC1, right? Agree?
Mhm.
And we are going in S domain. So let us write everything in S domain because we'll be using 1 by S block. So IR is nothing but V in minus V0 by R. Agree?
Yeah.
And IC is what? C dVC by dt. So it is S into C into voltage, which is V in minus V0. Is this clear? So basically what I have done is IC is equals to C into dVC by dt. So if you apply Laplace transform, we'll get IC of S is equals to S into C into VC of S. And VC is of nothing but V in minus V0. So that's why I have directly written that expression. So is this clear? Or any queries?
That's clear.
Okay. So now if I take common V in minus V0, I will have I in is equals to 1 by R plus SC into V in minus V0. So now if you calculate V in minus V0 is nothing but R by 1 plus RSC into IN. Basically everything is in S domain. So let me write. So we'll get V naught of S is nothing but V naught of S, or let us remove S domain. It might create confusion. So let us write V in is equal, sorry, we are writing V naught, right? So V naught is nothing but V in minus In into R by 1 plus RSC. So this is the expression that we got, right? So now, how can I implement this in MATLAB? So I can use a subtractor to subtract V in perform this expression V in minus I in into R by 1 plus RSC. But how will I implement R by 1 plus RSC in MATLAB? So we have to use the blocks, right? So my question is, how can you implement R by 1 plus RSC? So how can this be implemented? Without using transfer function. Yes, transfer function block is there. But say I want to use only the integrator. So how can I do that? Anyone, any idea?
You can write that in a like feedback output format, like A by 1 minus A, something like that. And use
Yes,
a
yes,
feedback loop.
yes. Very good. So basically, who was answering that? Rahul?
Shubhendu.
Shubhendu, okay, yeah. So what Shubhendu's idea is, we can use this control system block where we have this type of system. So this is a transfer function. So what he was trying to say is we can write in this format. So the input to output. So this is y, this is u. So y by u is nothing but g by 1 plus g h. So what he was trying to tell is we can calculate what is g, what is h, and then this can be represented in this format, right? That's what you are telling, right?
Yeah, yeah.
Okay. So now can we get any idea what is g, what is h from this expression? So can you predict what could be g and what could be h? Anyone?
The G may be resistance.
Okay, G
H
is
may be
resistance.
capacitor.
H may be.
Capacitor.
Okay, then what about S? Where will S go?
CS.
So like where should I keep S?
So if your R is G, then your
Yes.
GM equals to RSC, right? From there, you can evaluate your H to be SC.
Okay, so yeah, the first prediction is G is R and H is SC, right? So if I have to implement SC, then I have to use S into again C, right? But
Yeah.
is S block available in MATLAB?
Mm, I'm
S
not
is an
sure.
improper
That will
transfer function.
The
So
integrator.
yes, integrator is 1 by S. S is
So you can do one more thing. You divide numerator and denominator by some factor, some 1 by S or something. Then this will convert it into integrated related block.
yes, yes, very good. So directly looking at this expression, the main or the first thought would be G is R and H is SC. But nowhere we can use S block because S is an improper transfer function and that cannot be used to implement the block diagram. So what we'll do is we'll divide numerator and denominator by RSC. So this term will become 1. So I can simplify this expression and you can write it as you divide numerator and denominator by RSC. So then we'll get 1 by S into C by 1 plus 1 by S into C into 1 by R. Is this clear? Basically, I have written in a different way. I have divided the numerator as well as the denominator with RSC. So the numerator will become 1 by SC, denominator will become 1 plus 1 by RSC. So now that I have segregated, so from this, you can understand that your G, what is your G? Your G is 1 by S into C and your H is 1 by R. Now I can use integrator block to implement this. And what is your input U? Your input is I in, right? So that's why my I in into this transfer function will give me this term. Now I have to subtract this from my V in to get V0. So is this clear how we are converting everything into integrator terms so that we can implement it using the integrator? Clear for everyone?
Yeah.
Okay. So now let us draw the entire block diagram. So my input is I in, then we have an integrator block, which is 1 by S multiplied by a gain, right? So I'm using the same shape as MATLAB. And then we have in the feedback, what do we have in the feedback? We have 1 by R. So we'll have another gain term, which is 1 by R, right? So this is the direction, and this is plus, this is minus. So now this output is what? Minus I in into, this output will be I in into R by 1 plus RSC. So now I have to subtract this from V in. So we'll be needing another subtractor block. And say V in is a constant block. Now my output is V0. So this is my V in, and this is plus, this is minus. So what is my V0? V0 is nothing but V in minus whatever this expression. And what is this expression? It is I in into, because Y by U is G by 1 plus GH. So my output Y will be U into G by 1 plus GH. And what is U? I in. So my input is I in and the transfer function is R by 1 plus RSC. So I have used integrator because this is wrong. I cannot use SC. So this cannot be used because S cannot be used. S is also not practically implementable because it's an improper transfer function. This is a proper transfer function, strictly proper. So I can use this. So this is how you should implement in the MATLAB and how you will create the blocks and then you can run. Is this first question clear for everyone? How to implement this using a block diagram? So we have converted everything into S domain and then we have solved. Is it clear? Please confirm if you understood. If you have any queries, then you can ask. Else we can proceed to the next question. Is it clear for everyone? Also, you can mention
Yes,
in the
it's clear.
chat if you okay. So in the next question, this is S, this is S bar. So we are asking what is Vx in the following circuit. So when S is on, what is Vx? So we are asking what is Vx. So there can be two conditions. S is on. When S is on, what is Vx? When S bar is on, what is Vx? So when S is on, this is the circuit, right? So when S is on, how will the current flow? Current will flow in this direction, right? And this is 0. This is ground. So what will be my Vx? Anyone?
IL into R1.
IL into R1. Very good. So my Vx will be IL into R1 because it is ground and Vx will be at a higher potential. Very good. So it is IL into R1. Okay. Now S is off, S bar is on. So the connection will be, sorry, this will be the connection, right? And this is how current flows. So now what is R Vx in terms of V0 and other expression. Vx. We don't want in terms of VL because VL is also not known. You can tell in terms of V0, IL, R2, anything.
V0 plus IL into R2.
IL into R2. Very good. So it is V0 plus IL into R2. So Vx is this expression during Q equals to 1 and during Q equals to 0, this is the expression. So now if I am asking what is the value of Vx in terms of Q, so then we can write something like this. So when Q is 1, Vx is IL1 into R1. When Q is 0, it is V0 plus IL into R2. So if I'm asking for the expression, then I can write it as VL is equals to Q into IL R1 plus 1 minus Q into V0 plus IL into R2. So if you substitute Q equals to 1, then VL will be IL into R1. If you substitute Q equals to 0, it will be Vx is equals to V0 plus IL into R2. So is this also clear? How we are getting in terms of Q? Basically, we have to see when the S is on, what is Vx. So this is this switch is shorted and IL is flowing through R1. So Vx is nothing but IL into R1 when Q is on. When Q is off, this is shorted. IL is flowing through R2. This voltage is V0. So Vx is V0 plus IL into R2. So now I have to write a single expression in terms of Q. So when Q is 1, this is Vx. So Q into IL1, IL into R1. This is Vx when Q equals to 0. So I have to multiply by 1 minus. So is this clear how we are getting this expression?
Yes.
Okay. So if I ask what is the value, average value of Vx, then how will you calculate? If I'm asking average value of Vx during this time, then what we'll do, we'll check what is the time period. So this is during DTS, this is during 1 minus DTS. So now can you tell me what is the average value of Vx?
So Q will be replaced by D and 1 minus Q will be replaced by 1 minus D.
Yes, very good. So basically how we are getting, we are calculating the average. So 1 by Ts into D into Ts into ILR1 plus 1 minus D into Ts into V0 plus ILR2. Now if we calculate or if we simplify, then we'll be getting average Vx is nothing but D into ILR1 plus 1 minus D into V0 plus ILR2. So this is the expression that we'll be getting if we are asked about the average value. So is this question also clear for everyone? If you have any queries, please ask. Else, clear? Okay, if you don't have any further queries, then we can move to this question. So in this question, can you calculate voltage gain and efficiency? It is very simple and straightforward. So first of all, what is V0 in this question? Value of V0?
5 into 10 by 15.
Okay, simplify and tell me in P by Q form, what is V0? Tell in
10 by 3.
Okay, yeah. So V0 is 10 by 3 ohm. Everyone agree?
Yes.
So now what is the voltage gain, kV, and what is the efficiency? What is kV?
2/3.
Yes, V0 by Vin, which is 10 by 15, which is 2 by 3. Very good. And what is the efficiency?
33.
Same, right? Same.
Same. Same. So efficiency is
Oh,
basically 2 by 3. If we are talking about percentage, we'll do into 100. So it is 66.67%. Right? Right?
yes.
Okay. So now if I ask what is the output power, P naught, what is P naught?
It will be V square by R. So output is 10 by 3 square
10 by
divided
9.
by 10.
10 by
Yeah.
9.
10 by 9, right?
1.11.
Yes, 1.11. Now if I ask calculate the losses in the circuit, so I want P loss.
That will be input power minus output power, right? So that will be, or you can do like a current multiplied by that 5 ohm resistance.
Yes. So can you calculate the current? Okay.
Point,
Maybe I'll ask
0.555.
what is current in the circuit? I know.
5 by 15. So 5 by 15 is 1/3.
So now calculate the P
0.3.
loss.
0.3 into 5
Yes, 0.33.
is, yeah, into 5 is
What is power? I square or IR?
1.6. Powered by I square.
5 by 9.
5 by 9. Yes, 5 by 9. Okay. Now if I ask you what is the input power?
Uh, 5 by 3.
1.66.
5 by?
Yeah,
5 by?
1.66.
Yes, 5 by 3 or 1.66. Very good.
1.66.
Yes. So this is how we can calculate. Similarly for shunt, if they have asked, so you can use this type of expressions. So it is also same. You just have to get the expression and then you can calculate output power, current. This will be given what is I naught, what is I in, what is loss, what is input power, output power. Similar way. Only the expression will vary, but the methodology remains the same. So I hope this question is also very clear, simple and straightforward. Shall we move to next question?
Yes.
Okay. So this is the question. Kindly read the question that we can solve. So the question says, identify the following circuit. So first of all, what is this circuit? Then we have to calculate the duty ratio. When the input is 10, output is minus 15. Input is 10 and output is minus 5. And then load resistance is 10. What is the average inductor current for both cases? Okay. So first of all, can you identify this circuit? Which circuit is this?
Buck boost. Buck boost.
Buck boost. Yeah, very good. So the circuit is buck boost. And what is the input output relation for buck boost converter?
Minus D by 1 minus D.
Minus D by 1 minus 2. Very good. So let us use the expressions that we have derived earlier. So this is the expression, right? So minus D by 1 minus D. and IL is d into V in by R into 1 minus d square. So let us use these equations. So first case, in both the cases, resistance is 10 ohm. One case, V in is 10, V naught is minus 15. So let us do for case 1. So these are the expressions that we have. So case 1. So in case 1, in both the cases, input is 10, output is minus 15 in the case. So input is 10, output is minus 15. So can you calculate what is duty ratio in this case? Someone please calculate and tell me what is duty ratio. This is V0.
0.4.
0.4. Okay. Others also please calculate and we can cross check whether it is correct or not. So if duty ratio is 0.4 and the load resistance is 10 ohm, can you calculate what is IL? So it is D into V in by R into 1 minus D square. Also, please check whether D is 0.4 or not and let me know. So has anyone calculated?
D is
what
0.6.
0.6 for the first case?
Yeah.
Okay, let me calculate. V0 by V in is how much? Minus 3 by 2, right? So minus 3 by 2 is equals to D by 1 minus D with a minus. So 3 minus 3D is equals to 2D. So D is 0.6, right? Everyone?
Mm.
Yeah. So 0.4 is wrong. D is 0.6. So can you calculate IL now? So IL is nothing but D into V in, which is 10 into 0.6. So 6 in the numerator. In the denominator, we have resistance 10 into 0.4 square. So 0.4 square is 0.16 into 10, 1.6. In the numerator, we have 6. So 6 by 1.6, which is 60 by 16. So if we divide by 4, it is 15 by 4, right? Everyone agree? Or did I make it?
3.75.
Sorry, 3.75. Yes,
3.75.
yeah, very good. So 3.75 amperes. What about second case? What is D? So it is minus 1 by 2 is equal to minus D by 1 minus D. So 1 minus D is 2D. D is how much? 1 by 3, right?
33%.
Yes, 0.33. So D is
0.33.
0.33. Yeah, very good. What is IL? IL is D into V in, which is 1 by 3 into 10. So 10 by 3. If we calculate 10 by 3 by R into 1 minus D square. R is 10. 1 minus D is 2 by 3. So 4 by 9. So 10 get cancelled. 9 by 12, right?
0.75.
0.75. Very good. So IL is 0.75 ampere. So this is how we calculate. First, we have to identify the circuit. Then we can get the voltage relation. Using the voltage relation, you can also calculate IL. But because we have derived it anyways, I have directly used the expressions. Then in the question, they have given load resistance instead. What is the average inductor current for both cases? So duty ratio is 0.6 in the first case and 0.33 in the next case. IL is 3.75 amperes in the first case and 0.75 amperes in the next case. So if you see, for higher voltage, inductor current is more, also duty ratio is more. Here it is 0.33 and here it is 0.75. There is not linear dependency because the function is d by 1 minus d, which is non-linear. So this is also non-linear. So actually you can plot d and 1 minus d and see how V0 is changing with respect to d. Similarly, how current is changing with respect to d. So that you can use online plotter or also using MATLAB you can do. but this is the whole idea. So this is the like today's session. We have thoroughly discussed about few converters. Also, we have solved a few problems. If you have any queries, then we can discuss. If you don't have any queries, then we'll wind up this session, and again we'll meet next Monday. So people who are interested can also join tomorrow's session. Any queries till now?
No.
So yeah, I hope this session was helpful. If you want me to incorporate anything, then you can give me feedback, which I'll consider in the next session. So any feedback you'd like to give? Anything that if the pace is slow, if the pace is fast, you want me to solve more problems, then we can accordingly adjust. If no feedback, that's also okay. Okay, thank you, sir. Arun is saying. If you have any feedback, you can give, else we can wind this session.
Teja, a little more problems would be nice. I think
Okay.
theory part already is being covered in that
Okay,
one. So
okay.
maybe if a little
So-
more problems would be helpful.
Okay. So next week I'll minimize the theory and then we'll solve more problems. Okay. Yeah, that is
Thank
a
you.
good
Yeah,
thing.
that'll be great.
Yeah. Thank you. Thank you for the feedback. Okay, if you don't
Be on
have
the same
yes,
week one content only, right?
Yes, week
Like
one.
tomorrow's,
This is week one.
it'll be on
Tomorrow is
week one
also
only.
week one.
Okay,
Yeah.
fine.
Okay, in that case, we can wind this session here. If you have any further queries, you can ask in the YouTube comment section of this video. Also, you can ask Kelvin tomorrow. So thank you for joining. It's a nice session, and I wish you all the best for your assignment 1. See you again next Monday, 6 to 8 with week 2. Okay, then good night, and I'll try to upload this by today night. See you in the next week. Good night, everyone. I'll end this meeting.
Thank you. Good night.
Yeah, thank you.
Yeah,
Good night.
thank you.
Thank you.